All righty. Hard to believe. We're down to our last 4 lectures, or maybe 5, depending on how you count them. The one thing I wanted to point out is the topics that we've been discussing are not really in your textbook anymore. For some reason, that textbook is missing networking. So I'm going to try to put papers up and other reading for you guys. Okay, settle down. Shh, I realize that it's so sunny out that everybody is outside. Woo! All right. So if you remember from last time, one of the things we talked about was how to get durability in a grand scale, okay? And I just wanted to put this graph back up to make sure that we knew what it was about. We talked about erasure coding, and we specifically talked about Reed-Solomon codes. And this particular graph, I didn't get a chance to explain as well as I wanted to last time, shows you an interesting fact. So what you're going to assume here for a moment is that I have data I really want to preserve, and I have lots of options on how to do that. And one of the obvious options is just to put copies out there on servers, right? I just copy it. The other option is to use erasure codes. And what this particular graph shows you is for the same total number of bits of storage out in the net, which one does better? Okay, the assumption is, for instance, if I've got some data, I copy it on 4 servers. That's this top line here, and the repair time on the bottom says this is the number of months I wait before I go out and make sure that I still have 4 copies. Okay, so every, say, 6 months I refresh my 4 copies to make sure there's always at least 4. Is everybody with me on that option? Now, the alternative would still have a factor of 4 total overhead storage, but I would use erasure codes where I would send out 64 fragments, any 16 of which are sufficient to reconstruct. Same total size. That's this bottom graph. If we were to slice along, say, the 6-month time frame, what you would find is that if I refresh every 6 months, with 4 copies, I lose 3% of my blocks a year with certain assumptions. With fragmentation, I lose 10 to the minus 33% of my blocks a year. Same data size. So as you can see, erasure coding is pretty powerful. Okay, now, of course, there's assumptions about independent failure and so on. If you put all of these fragments on the same disk and it gets run over by a bus, doesn't help you any. Right? Okay, good. Now, by the way, I did split the one really big Reed-Solomon slide into 2 slides and added a little information on last lecture if you guys want to check it out. The other thing we talked about is we talked about transactional mechanisms for ensuring consistency. So this is a different requirement on file systems. You'd like, despite failure, you'd like the file system to stay consistent. And we talked about a bunch of options, including copy on write file systems, but ultimately, the most general is to use a transaction approach where you do start in the log, you do a bunch of operations in the log, and then you do commit. And if you don't get to commit and you crash, then none of what you did gets reflected in the file system and it stays consistent. Okay? And I talked a little bit about the difference between journaling and log-structured file systems. Journaling is pretty much what you're going to run into these days, where there is a log that's being treated as a journal, and it's purely there to give you transactional updates to the file system. Log-structured is actually kind of cool. It's a notion where the data itself just always stays in the log. So you never remove it from the log. In the journal case, there's a file system just like we're used to with inodes in the same format you're used to, and the journal is giving you transactions. In the log-structured case, you're just writing this huge log that just keeps spiraling in the disk, and the top-level directory points to some inode that the latest version of which is in the log, and then it just points to the log. Okay, so that's the main difference. And I did have a good question during office hours today about this. I wanted to point out that the specific example of using a log that we showed last time, is what we'd call a redo-only approach where the only things you put in the log are idempotent operations of how to apply changes to the file system. It doesn't assume that you can have interleaved transactions going on simultaneously. So if you have two people writing, you got to put the first set of the first transaction down, then the second, and so on. A lot of file systems do it that way just because it's simpler. It means that all of your entries are only redo entries. If you want to do something like a database and come to take 262 with me, we'll talk about the general Aries way of doing this. Then you not only have to put redo entries, you have to put undo entries. But anyway, this what we talked about with the journaling file systems applies to a whole bunch of existing file systems you probably use every day. Question, yes?
Right. In the second major bullet point, you said in the log structure file system, data stays in log form, but in the journal file system, logs used for recovery. Is the difference just in the journal file system, logs are just kind of there, like not really primarily used?
No, they're used all the, no, okay, so your question is, in the journal case, is the log not really used? No, the log's always used. It's just only used long enough until you can be sure that the file system's been updated atomically. And so you always put stuff into the journal so that if it crashes, things that are in the journal won't be applied partially, and you'll still have a consistent file system. So the journal's always used, but it's being used to help update the file system. In the case of the log-structured file system, things are not laid out in track groups, et cetera, like we talked about. Instead, they're just literally on the log, and the inodes that are in the log point to other blocks that are in the log. It's a little, now that you ask me this, I should make sure that we have the original log-structured file system paper on the resources. If anybody would want to read it, I'll put that up. Okay? It's less common than the journaling. Journaling is much more common. Can anybody think of a great reason why the log-structured file system is a little less popular for mostly read application? It's great for locality on writes, but the reads get spread all over the log depending on when you wrote them, and so the read locality is really bad in a transactional file, in a full transactional file system, log-structured. Okay. All right. So, where were we last time? We were talking about this. You've got all of the mechanisms in the term up till now on how to understand the interior of the file system, the interior of the operating system and file systems in little devices. Now we're going to put a bunch of them together to make cyberspace. And what's nice, this particular spectrum from these little tiny robots that are made in these are micron-sized things made by laboratories here at Berkeley, all the way up through the cloud, super big clusters that Google and Amazon and IBM and all of those folks have. Together, these all interact with each other, and they're really one large computer. And the question is, how do you even make that work? So think about all of the trouble that we went to try to figure out how to schedule things properly and put in atomic sections with locks and make our file system consistent. Imagine all that applied to the global scale, and probably it boggles the mind. How can you possibly make anything like this work properly? Okay, and today I'm going to start us down that path of talking about distributed applications that are spread more widely and that can make decisions that are actually not corrupt decisions. So that's an important question. By the way, lots of smart things these days, okay? Everything from these little tiny devices on through cars, which have hundreds of processors in them, on up through refrigerators and big machines spread across the globe. Probably your watch, like Fitbit, right? I have a Fitbit, got a processor in it. Okay, everything's tied together. All right, so let's actually try to understand a little bit about terminology here. So what's the difference between centralized and distributed? So the centralized server system is the one that you're probably most familiar with thinking about. And that's a pretty simple idea where there is a server, which is probably a single machine. It might be a couple of small machines in some locale, and a bunch of clients. And basically, all the major functions are performed by the single physical computer at the center. And and the clients are asking the server to do something for them. Now, in fact, cell phones pretty much work in that mode, where your local phone talks to something in the cloud owned by your cell phone company, and that's a client-server model. Okay, so that's pretty common. The positives of this is it's very easy to think about synchronization when there's only one thing in the middle that really has the final say on the data. More interesting is a distributed system where it's physically separate computers are working together on some task. And in the early kind of models, you had a cluster with a bunch of things on it, and actually a lot of the cloud storage area, cloud services in Google and Amazon also have clusters that are in a rack or what have you. But later models went to what was called peer-to-peer systems, in which these individual components are spread across the network, and they're all kind of equally participating in this network, and together the whole is greater than the sum of its parts. Okay, and that's the really interesting thing about peer-to-peer technology. And I would say that this conception of peer-to-peer really only started in the early 2000s. Okay, but it has since evolved quite a bit. So are there any questions? So distributed systems are ones where all the major functions are distributed, and we're going to try to see what we can do to make that work. Questions? So, what's the motivation for this? I mean, why do we even want distributed systems? Because, heck, you look at this one on the left seems simpler. Okay, and the one on the left is simpler. Okay, so why would we even be tempted? Well, for one thing, we can imagine it might be cheaper and easier to build lots of simple computers and tie them together. This, in fact, was the whole premise behind RAID, okay, where the individual disks were cheaper and simpler, but together you got a powerful disk out of it. Same idea here. It's easier to add power incrementally. So when you have a really big supercomputer, you really can't just add things to it. You got to go to a bigger supercomputer. Whereas in a peer-to-peer or distributed model, you start adding computers or pieces to it, and things get incrementally more powerful. The other interesting thing here is that if this is a network formed by, say, all of your classmates together, and together you're providing some service, what's interesting about this is you can contribute to the service but still retain full control over your piece of the hardware. There's something appealing about that, okay? The other thing is collaboration typically is much easier for users to collaborate in a system which is distributed by its nature, where the network is just another part of the system. So the promise of distributed systems is really higher availability. Why? Because there's so many pieces, it's likely to be up. One of them's likely to be up. Better durability. Well, you have copies of things or fragments of Reed-Solomon coded stuff all over the place, harder to destroy your information. More security. Well, this one's a little bit trickier, but let me make the argument here. Each piece is smaller and simpler to make secure because it's not a really big system. Now, that one you might question me on a little bit, and I'm going to question myself in a couple of slides. But the promise here is that maybe we can get something by combining a lot of little things. Now, the reality, of course, is not that way. So typically, you've got worse availability. There's this famous quote from Leslie Lamport, my favorite quote in all systems. A distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. Okay? How many people have experienced that? You guys? Actually, you probably didn't know. You just thought it didn't work, right? Worse reliability. Well, you can lose data if any machine crashes in some of these systems because things just get corrupted. Worse security, of course, is anybody in the world can break into your system. So the reality of distributed systems has not always been great, but we've been making incremental progress and things are getting a lot better. The other thing that's really hard is coordination. This idea that a bunch of computers together can make a big decision is actually more difficult. Okay? Because you have to somehow coordinate multiple copies of the shared state. What would have been really simple in a centralized environment, it actually becomes difficult. So in a centralized environment, let's say you have one lock. You grab the lock, you update the state, you release the lock. That is consistent, right? In a distributed system, there is no one lock because everything's all over the place. So how the heck do you even think about consistency in a situation like this, all right? And, of course, what really rears its ugly head, especially over the last, I would say 5 years, but certainly decade, trust, security, privacy, denial of service. All of these things are problems here, right? Many new variants of problems arise because we've distributed. I don't know, can you trust the other members of a distributed application enough to even perform a protocol with them? I kind of came up with this afternoon. The corollary of Lamport's quote is, a distributed system is one where you can't do work because some computer you didn't even know existed is successfully coordinating attack on my system. Okay, so it's not that something's down, it's that something's up. And as a result, the thing doesn't work. All right, now, that's Leslie Lamport, by the way. You should Google him, by the way, because he's got a whole bunch of really great quotes. He's a quote maven. Great quotes. So distributed systems. What are some goals we might want? So first of all, we'd like to have transparency, which is the ability of the system to mask its complexity above a simple interface. So we want it to be essentially transparent. So what are transparencies we might want? One, location. You don't really want to know where the resources are. You just want it to work properly. Okay, we've all gotten used to cloud storage, but I'll tell you, when I first started the Ocean Store project in the early 2000s, I had lots of people, I'm not going to store my data out there in the cloud. I don't trust it. Okay, migration. We'd like the resources to move so that, when things fail, other things take over. It just kind of works. Replication transparency. Wouldn't it be nice if I didn't have to know how many replicas there are in order to make sure that things don't get lost? And the replicas don't get in the way of what I'm doing. Concurrency. Well, maybe I don't need to know how many users there are in the world working this system. Parallelism. Gee, the system might be able to throw a few extra processors at it and make it faster without me having to do something about it. Fault tolerance. Wouldn't it be great if the system can hide when things go wrong so we don't get into Leslie Lamport quotes? Okay? So transparency and collaboration basically requires some way for different processors to communicate with one another, of course, and that's going to lead to networking. Now, we're not going to go into the depths of networking today. We're going to actually sort of use it. But what are some definitions that I'm assuming you all have here? So a network is a physical connection that allows two computers to communicate. A packet is a unit of transfer. Okay, network carries packets from one CPU to another, routes them across other networks. The destination gets an interrupt when the packet arrives and processes it. Okay? The last thing is a protocol, which is an agreement between two parties as to how information is to be transmitted. Okay? So these are pretty simple, and they're things that you've run into already this term. So what is a protocol? So there's a little cloud, which represents the network, and we have some protocol exchange. So a protocol is basically an agreement on how to communicate, including syntax. How is the communication specified? What's the format, ordering of messages sent and received? And semantics, which is what does the communication actually mean? And, what actions are taken when you transmit, when you receive, or when a timer expires. It's described formally by a state machine, often represented as a message transaction diagram, and it can be partitioned into multiple state machines. So one way to look at a protocol is there's two state machines on either end, and the messages going back and forth are all about synchronizing those state machine transitions so both sides know what's going on. Okay, and there's a lot of classes around here that will talk about that sort of thing. The most important part about this is that the protocol is specified in a way that tries to make this work seamlessly, and typically there's some sort of stable storage underneath the covers that makes sure that in the case where one or the other end fails, you can come back up and pick up somewhat where you left off. So the way you get a really good protocol to work is not only is there state machines on either side that are working together with each other, but there is some stable storage, be it disk, flash, etc. Okay? And a couple of things we're going to talk about today fall into this rough category of state machine exchange with stable storage. Questions? Okay, so here's an example. You're going to use the telephone. You pick it up. You listen for a dial tone or something. See that you have service. You dial. You sure hear ringing, right? So these are all a set of things at one end. Other end says, hello. Hi, it's John. Well, it's me. I don't know. What's that about? How many people say, hi, it's me? I find myself saying that sometime. I'm not sure what it means exactly. And then, hey, do you think of blah, 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 blah? And then another protocol here would be, yeah, blah, 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 bye, bye, hang up. So you've all probably had this conversation this afternoon with somebody, right? Especially the blah, 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 blah part. But notice that there is a protocol here where you go from ringing to a hello to a hi, who it is, or do you think something? Yes, I do. Hang up, or bye, hang up, hang up. So now there is actually direct analogs of some of these steps in TCP/IP in terms of establishing and breaking down a connection, but this is an example of a protocol. And part of what you have to do when you're talking about a distributed system is how do you specify the protocol, and is the protocol functional under failure? Is the protocol functional when a malicious person tries to get in here, right? So during tax time, you probably haven't gotten this yet, but I got a lot of phone calls. Do not hang up. Please call us immediately, because otherwise we are going to send local law enforcement to your house to get your tax ID numbers. Anybody get any of those phone calls? Yeah, a few of you. There is a malicious phone call which is not correct, but how do you know it's not correct? And especially when you get into the computer area, it gets pretty tricky to know that the protocol is not correct. Okay, so one of the big problems with global communication is really one of matching of disparate functionality. So sort of you have at one level you've got applications, Skype, SSH, NFS, whatever, and then you got transmission types like coaxial cables and fiber optics and whatever. And how do you make this work? Do you have to give a different interface when Skype talks to a cable versus a fiber optic system? Think about that for a moment. That would be pretty bad, right? Many different applications, many different network styles and technologies, wireless, wired, optical, etc. How do we make this mess work? Do we re-implement every application for every technology? And I hope by now, at this point in the course, you're all saying, no, of course you don't, right? That would be a bad idea. What do we do instead? Standardize APIs, right? Okay. Like, for instance, here we add packet radio. We really don't want this n-squared growth in complexity. So the Internet, which, how many people have taken, 168 or other networking classes? Okay, good. What do? We put a standardized API in the middle, and that intermediate layer gives us an API that provides a set of abstractions for network functionality. And so a new app or media is implemented only once by going through the proper API. And variations on add other things at the bottom. We can add new apps. We can add new technologies. And this all kind of works because we picked a good narrow waist technology in the middle. And so the goal of doing distributed systems in a way that works well is really about picking APIs. Now, you've run into a lot of these APIs already when we talked about how device drivers works, right? There's the open read, write, close API that really is a standard communication protocol between users above and devices below, and that API is embodied in the system call portion of the operating system, and that helps do this kind of matching when it comes to devices. So our goal, of course, is going to be reliable communication channels, and we'll talk more about that next time. But let's assume that we've somewhat solved this problem. So this is the so-called narrow waist hourglass, which you've all seen probably in one of your classes. But down here in the middle portion there, that is IP. Above, you have protocols that have reliability like through TCP, but then you can put applications. Below, you've got packet transfer, transferring IP packets. This is pretty amazing and robust design that has basically been responsible for the internet taking over the world, okay? Because you can have companies innovating at a lot of levels underneath and companies innovating at a lot of levels above, and they all talk to each other properly. That's pretty amazing, and it's worked really well. Okay? So we're going to talk a little bit about this, but not a lot today. So what are some implications of this? So there's a single internet layer, allows arbitrary networks to interoperate, and any network technology that supports IP can exchange packets. That's pretty cool. It allows applications to function on all networks. Applications that can run on IP can use any network. Supports simultaneous innovations above and below. Changing IP is challenging. Okay, IPv6 has been like the running joke about networking for the last 20 years, right? Oh, IPv6, it's coming. Yeah, it's coming next time. No, it's coming in a decade. No, it's coming in whatever. It's almost here. Well, I think it actually, we finally gotten to where I think it's really happening, but it's been 20 years of saying it's going to happen. So that piece in the middle is pretty hard to change, but things above and below are very flexible, and that's why this has worked out so well. Okay, so layering has a bunch of drawbacks, right? Layer n may duplicate layer n minus 1 functionality, or layers may need the same information. So if you put a bunch of layers in, then what you find you're doing is you're communicating all the information up and down, which is giving you essentially the same effect as you had with that n squared problem before. So you got to be very careful of your layers. Okay, obviously layers can hurt performance. Some layers are not always cleanly separated. And the other thing that's a little funny in the network in particular is each layer you wrap a header around. So you have the IP, you wrap, TCP around it, and then you wrap something else, and then you wrap something else, and these headers end up being much bigger than the data that's being transmitted. Okay, and especially with internet IoT devices, where you have something that's trying to send a single temperature reading, and you wrap, 512 bytes of header around this little 3-byte, 4-byte temperature. Okay, so that's the cost of layering. Okay. All right. Administrivia. So last midterm's coming up, 5-2, surprisingly in a couple of weeks. It's hard to believe. You can have 3 handwritten sheets of notes, both sides. We're going to focus on material from lectures 17 through 24, but all topics are fair game. Don't forget to do group evaluations. Your TAs may reach out to you. I think a couple of folks misread the 20 points per member distributed to members. They may reach out to have you redo that. But don't forget to do them. Very important. We mentioned the optional homework 4. I think it's essentially done. It will give you a chance to play with Go and do two-phase commit, which is what we're going to be talking about today. So watch for it if you feel like you really want to do something else, different, new, something additional. Okay, I think that's all the administrivia I had for today. Are there any questions? Okay. So what I wanted to do today as sort of the next topic is I want to talk about the end-to-end arguments and systems design paper. This is sort of the sacred text of the Internet. Anybody who talks about the Internet or who has a specialty in the Internet always likes to talk about and throw about end-to-end arguments. How many people have heard about end-to-end arguments? Okay, several of you. So, as with any sacred text, there's lots of disputes about what parts of it mean. Everybody cites it as supporting their position, this kind of thing, right? But the simple message is that some types of network functionality can only be correctly implemented at the endpoints. Things like reliability and security ultimately can only happen at the endpoints, and that's why it's called the end-to-end argument. This is a very simple paper. I put it up. I think you'll enjoy it. Think of it as a philosophy paper, the philosophy of distributed systems. And read it through, okay? It's a very quick read, and we always start out with that in 262 as well. So because of this simple idea, the simple message, end hosts can basically satisfy all the requirements without having anything in the network that's doing anything special. Not any reliability, security, etc. All of that can be done by the end hosts. And so the end hosts will, or maybe we'll say must, do so since they can't rely on the network's help. The fundamental premise of IP is it's an unreliable protocol. Things can get corrupted. You're not even guaranteed a throughput of the network, and therefore you have to verify everything at the end host level. Okay, and that's very simple. Therefore, don't go out of your way to implement them in the network. So that's the basic philosophical premise. Gee, you got to do it already. Don't make the network complicated because the end host still has to do all this stuff. Now let me show you a simple example here. So this is the reliable file transfer example that's actually in that paper. So you've got host A and B are transferring a file. Okay, so what happens here? We've got the file, goes up to some application level, which is doing the transfer, comes back into the operating system, gets sent across the network, goes back up to the application layer, gets written to the file system. So the first solution to reliable transfer is you make every step reliable. So when it goes from the disk to the application, you make sure that it's never lost. When it goes from the application to the operating system, you make sure that that's perfect. It goes from the operating system through a whole bunch of hops in the network. I've simplified this. You make sure every hop is reliable. Then every other hop coming up is reliable. And then you concatenate this together, and you got a reliable transfer, right? Okay. Well, the problem with this is, first of all, if these are not 100%, then each of these red things might be like 0.99999% perfect. What happens when you concatenate a bunch of imperfect things together? You multiply their probabilities, right? And very quickly you're down to 80% probability. Okay? The other thing is, if you forget anything in the middle and you don't make it perfect, then all of a sudden what you thought was perfect is flawed fundamentally. What's the funny example they give in this paper, which I think is fabulous, is they talk about the source code for the Unix operating system that's been transferred this way many, many times back and forth. And there was a bug in the routing code that every millionth byte would cause a little bit of a transposition in that byte. And so what happened was the source code went back and forth many times, and every millionth byte got swapped with another byte. Okay, so it was really not perfect, and you ended up with bad sources. Okay, that's not a good thing. So solution number 2 is you have an end-to-end check and try again if necessary. So basically, after it goes all the way through, you do a checksum, and you send it back. And the checksum is checked, and if it's wrong, then you go and do a retransmit. So notice that by doing an end-to-end check, checksumming it, and making sure that things got transferred, I make sure that everything in the path happened correctly. Because I'm actually checking the thing that ended up on the disk. Is it matching what was sent? And it doesn't matter if there was a router in the middle that was transposing bytes, that would come up as a failure of the transfer. The end-to-end argument would come into play. I'd notice that. I'd send it a second time. Okay, so this is not rocket science. It's a fairly simple argument, but it's very powerful. It sort of lets you focus on what really matters in your networking. Got to do it at the end-to-end anyway, so what do I actually have to do in the middle? I like to think of this also as the risk argument for networking. Okay, so I don't know if do they talk about the risk arguments in 61C? Not so much. Same idea there was you want to make sure that the whole stack matters with your instruction set. It was about instruction set design. Okay, questions? Now, solution 1 is incomplete. Because if the memory is corrupted or you have to do the check anyway. So checking everything all the way through is guaranteed to miss something. Okay, however good you are, you're going to miss something. Solution 2 is complete. The full functionality can be entirely implemented at application layer with no need for reliability from the lower layers. You could get garbage underneath. You'd catch it. You'd send it again. Now, is there any need to implement reliability at lower layers at all then? What do you think? Does this argument convince you guys that you never have to worry about reliability on an individual link basis? How many people think no reliability at all? Well, in principle, you don't need any reliability because you'll catch problems. In practice, what happens if it's so unreliable? What was that? Yeah, you got to keep retransmitting. You may never get it through, right? So there is a level of error where the ends can't do anything because the middle's so bad. And it's certainly the case that you could have more efficiency by putting reliability at the lower level. But the discussion here is understanding that trade-off, understanding you still have to do it at the end-to-end level, thinking about, well, can I put something at the lower levels to improve performance? Oh, yeah, but I don't have to be perfect about it. If I just increase the reliability a little bit, it might make a huge difference. Okay? So the end-to-end principle is really this. Implementing complex functionality in the network doesn't reduce host implementation complexity, still got to do it anyway, does increase network complexity. Probably imposes delay and overhead in all applications, even if they don't need the functionality. So the end-to-end paper also talks about this notion of, think about streaming videos. Okay, the streaming videos can be imperfect in what gets to the other side. What's worse than a slight bit flip in a video packet coming across is a delay in the video packet. Okay, that's worse. So a delay caused by the need to retransmit over and over again is much worse than sending slightly flawed video. Okay, and the end-to-end principle, they talk about this in the paper as well, which is very forward-looking for when it was written, is basically that everything that it goes through the network ends up using what you put in the network. Okay, whether it needs it or not. Now again, however, implementing things in the network can enhance performance in some cases, like over a very lossy link. Okay? Good? So, a conservative interpretation of the end-to-end argument is don't implement a function at the lower levels of the system unless it can be completely implemented at this level. Or, unless you can relieve the burden from the host, don't bother. Okay, that's the conservative version. A more moderate interpretation might be think twice before implementing the functionality. Understand the whole stack. If hosts can implement the functionality correctly, implement it at the lower layer only as a performance enhancement. Do so if it does not impose burden on applications. Okay, this is the interpretation that we're going to assume here. It's really about understanding the full system design and putting things carefully in the network. This, by the way, is very useful even as programmers on local nodes when you guys are doing your operating system code, right? Don't implement an enhancement in a performance enhancement unless it's really needed. What do they call that? Premature optimization, right? Just say no. Now, is this modern interpretation still valid today? Yes. But you got to think about some things that the network exclusively can help with, like denial of service, like privacy against intrusion. So perhaps there are things that can only be done well in the network and need to be there to help the end hosts, okay? Especially when you start talking about trust and privacy. Okay. Questions? So that's your philosophy for the night. Take a look at that paper. I highly recommend it. But now let's put that in the back of our minds as an important application or important philosophical point. And now let's talk a little bit about distributing our applications. So how do you actually program a distributed application? You need to synchronize multiple threads running on different machines. There's no shared memory, so you can't use test and set when you're building a distributed application. So, for instance, here's the network. Maybe I can send a message and receive a message. There's one abstraction, send and receive messages. So that's a little different from the way you've been programming distributed systems up till now, or been programming, threaded programs in your single machine. So what's interesting about message send is it's an atomic operation. Okay? It either makes it all the way there and the checksum is correct, or it doesn't make it there. So it either goes all the way or not. So it's atomic. And so you can construct all sorts of things out of that. The interface, sometimes there's a mailbox interface, which is a temporary holding area for messages, which is basically the queues at either side. You could think it's sockets at either side, kind of form one of the ideas behind a mailbox. There's a send message, which sends it, and a receive, which waits until there's a message and receives it. Very simple interface all around that idea of messages. Okay, and with that simple interface, you can build all sorts of cool stuff. You can even build shared memory out of messages such that then you can do your test and set at the shared memory level. Okay, I did that in a multiprocessor that I designed once where we had shared memory spread across a bunch of nodes, and the way you got shared memory was you had messages that sent and received all the changes back and forth for cache consistency. Okay, now, how do you use messages? Well, this API is a little bit less straightforward than you might think of if you think about it a little bit more. When should a send be done? When the receiver gets the message? There's an ACK there. Or when the message is safely buffered on the destination? Or right away if the message is already buffered on the source node? How many people like when the receiver gets the message as a return from send? Anybody? By the way, there's no right answer here. I'm just curious. How many people like the first one? Okay. How many like the second one when the message is buffered on the destination? Okay. How many like the third one right away if the message is buffered on the source node? Okay. Now, most of you didn't raise your hand. So how many people are not sure what they think they'd like? Okay. So each one of these has its pros and cons. I will point out that the first one here, when the receiver gets the message and there's an ACK received, seems like that ought to be a great way to build an application. But if you think about the end-to-end argument for a moment, the problem with that idea is I send it, it goes all the way to the other side, it gets in a buffer at the application level, at the receiver, and then I get an ACK, and what happens? That machine crashes, and the node never gets the message, or the application never gets the message, right? So you could go to a lot of work to make the first one happen and still not have the level of reliability you think you're getting. Okay, so as you become more proficient at building your distributed applications, which you will all do over time here, start thinking about what functionality do you really need in the network. So there's actually really two questions. Kind of when can the sender be sure that the receiver actually received the message, and when can the sender reuse the memory containing the message? So for instance, again, think about this first one. How do I make sure that I don't return from send until the receiver gets the message? Well, that may mean I have to hold on to the message locally and retransmit it a bunch of times because it maybe fails and I don't get an ACK right away. And then eventually I get an ACK, and at that point I can free up my buffer space. So a lot of intertwined questions. So Mailbox really provides a one-way communication from thread 1 on node 1 to thread 2 on node 2. And there's a buffer in between, which is the network. It's very similar to a producer-consumer. So you could actually, if you think this through, think about this as semaphores with V and P, where the message is being sent. Okay? Unfortunately, and in this case, you can't really tell if the sender or the receiver is local or not. So you could have a mailbox that basically sent a message from a thread on in one process to a thread in another process, and it went through a Unix socket and never left the node. That behavior wouldn't be any different, as far as the programmer can see, than going all the way over the network. Okay, except for time. Now, so let's talk about messaging for producer-consumer style. So let's use send and receive for a producer-consumer thing. So you might imagine, here's a producer, while one, prepare a message and send it. Consumer says, while one, receive, and this is blocking in our model, and we wait until something comes in, we process it, we get to the next one. This is, in fact, exactly the web server program that we started with kind of at the beginning of class, right? This is hopefully looks very similar. There's no need for the producer-consumer to keep track of space in the mailbox because that's handled by the implementation of send and receive. And next time we'll actually discuss the fact that one of the roles of the window in TCP is to help make producer-consumer synchronization work properly. Okay. But what about two-way communication? Well, you just put two of these together, one in each direction. And that gives you a request response where you read a file stored in a remote machine. So this one is closer to the web server case. It's often called client server, as I mentioned. So file service, you send a query that says like read rutabaga to the server's mbox. It goes to the other side. And then while I'm waiting for the response, I'm blocked in receive, and the response eventually comes back, and I can do something with it. What's the server doing? The server waits to receive the command, figures out what the command is, reads the file, sends the answer. And of course, there's loops here or whatever to make this go on forever. But basically, the way I got two-way communication is I had two one-way communications in opposite directions. Now, I realize that seems like a silly thing to say, but I thought I'd point it out. The network is not a two-way communication device. The network is a one-way communication device. Okay? And you got to make sure you got both directions. Yeah, question?
So with the client just repeatedly send the same exact message, so they can receive an actual response from the server, like how do you guarantee that the server is actually giving you the correct response?
So we will assume for now that send uses a reliable networking protocol and makes sure that it got there. And so you only have to send it once, and that receive is blocking and waits for it to come back, which is essentially what the socket API is like. So did that answer your question? Or? Yeah. So we're assuming that there's some reliability thing underneath that's going to help make this get from node to node. Now, of course, the one thing, echoing Leslie Lamport for a moment, channeling Lamport, there's nothing that you can know about, or there's no way to know for sure that once you've sent that request that the machine doesn't crash and you end up waiting forever. Okay, that's essentially the problem with distributed systems right there in a nutshell. It's because I can send and I can make sure it gets to the other side, but I can't be sure the other side is going to do something useful. Okay, and that's the channeling of Leslie Lamport. Okay, questions? Good. So distributed consensus making is such an interesting topic that it has been many papers written over the last 30 years about different ways for nodes that are spread across the network to come to a consensus. I wanted to make sure that we had an idea what it meant. So the consensus problem says all nodes propose a value. Some nodes might crash and stop responding, but eventually all the remaining nodes decide on the same value from a set of proposed values. So, everybody comes up with, I don't know how many slices of pizza they want tonight, and eventually everybody agrees on, we're going to get, or how many pizzas they're going to get, and eventually you all agree to get 2, all right? That's a consensus. Now, what do we mean when we mean distributed decision-making? Usually that says that you use some special values through your consensus. So like true and false. The distributed decision is this true or false? Or is this a commit or abort? That's a decision being made by everybody proposing values that the consensus algorithm then chooses one amongst them. Okay? Equally important, but often not mentioned in the same breath as consensus, but I'm going to mention it in the same breath, is, let's see if I can keep going without stopping and breathing, I'm going to say, nope, didn't make it. So it's very important to make it durable as well, because once you make a decision, if you immediately forget, then that's a problem, because you've made a decision, but nobody knows what the final decision was. You might not have made a decision at all. So this is the D part of ACID, right? So when we talked about transactions last time, we talked about durability. In a global scale system, what does it mean? Well, it means that the decision, once it's made, is kept durable, like with erasure coding, or a blockchain, or something that's guaranteed that the decision doesn't go away. Or maybe you've got local flash storage on every participant that writes the decision made there once it's made so it doesn't get lost. But you got to make sure there's a D. Okay, and it's often very easy to forget the D. Okay, don't forget the D. All right. And you know what? They say the offense always comes from the D, right? So, very important. Okay. You guys are all watching the Warriors tonight, right? Yeah, okay. They need you. So why don't we take a brief break, and then we're going to come back and we're going to talk about some distributed consensus algorithms that are quite interesting. Okay. So let's start with a pretty simple idea here called the general's paradox, which is as follows. The general's paradox involves generals, and the constraints of the problem is that there's two generals and they're on separate mountains. They can only communicate via messengers. See, these are the messengers. They're on horses. And the messengers can get captured. So that is a lossy network. Okay? Problem is you want to coordinate an attack. If they attack at different times, they all die. If they attack at the same time, they win. Okay, now, two generals. So we're only going to try to solve this problem for two. Okay, is everybody with me? Two. That's not three. Okay? And it's named after Custer, who basically died at Little Bighorn because he arrived a couple of days too early. But the question is, can messages over an unreliable network be used to guarantee that two entities do something simultaneously? Remarkably, the answer is no. Okay, even if all the messages get through, okay, here we have our two generals. Yeah, 11 a.m. okay? Yeah, 11 works. So 11 it is? Yeah, but what if you don't get the act? Now, what you do is, if there's a possibility of lossiness in here, the problem is that you never know for sure that your message was received unless you get an act, but then the problem is the other guy doesn't know that his act was received. Okay? So there's no way to be sure the last message gets through. And of course, in real life, you use a radio, which is an out-of-band communication mechanism. Custer did not have radios, right? So clearly we need something other than simultaneity as our goal. Okay, so, basically message loss leads to the inability to pick a time that everybody agrees on. And there's been many attempts to solve the general's paradox in various ways, and you can't solve it. Okay, so the question would be, can we do something slightly different? So we can't solve the general's paradox, but let's solve a related problem, which it turns out is mostly good enough. It wouldn't have helped Custer, but it's a distributed transaction where two or more machines agree to do something or not to do it atomically. Now, there's no constraints on time, so we're not going to actually try to make it happen in a particular time, but what we can say is that it will eventually happen for sure. Do you see the difference on this? We're removing time from the equation, okay? And the most famous and simplest version of this, called the two-phase commit protocol, it was developed by Jim Gray, Turing winner. He was also the first Berkeley PhD, 1969, for CS. And there's a lot of very important database breakthroughs from Jim Gray. So he is an amazing person in the database field. Now, as you're probably all well aware, he unfortunately disappeared in his boat, and they never found him back in 2007. So that's Jim Gray. But he is definitely one of the lights of Berkeley that got snuffed out too early. So what's a two-phase commit protocol? It basically keeps track of whether a commit has happened in the persistent log. If a machine crashes, when it wakes up, it first checks its log to recover the state of the world at the time of the crash. So notice that what I've slipped in here quickly without even saying it is I put the D in, right? Durability is a fundamental part of this. Okay? There's two phases. That's why it's called two-phase commit. The prepare phase, where the global coordinator requests that all participants promise to commit or roll back the transaction. Participants record promises in the log, and then they acknowledge. And if anyone votes to abort, the coordinator writes abort in its log and tells everybody to abort, and everybody records abort in their log. The commit phase is if everybody says okay, after all the participants respond that they are prepared, then the coordinator writes commit to its log, and then it asks all nodes to commit, and they respond with an ACK. And after it receives its ACK, the coordinator writes got commit to the log. Now, this seems very simple, but notice there's a lot of writing to the log. And the reason you write to the log is to make sure that if a decision is made, like to commit or abort, there's no way for participants to crash and come back up and do something different. Okay, so the way this protocol is set up is it records all the important parts of the state at the right times. Like, for instance, if a participant decides they're going to commit, then they're going to write commit in their log, and then they're going to respond. So there's no way for the coordinator to hear about, they're going to commit, where the other guy didn't write, where the participant didn't write commit in their log and subsequently crashed. There's no situation where somebody says they're going to do something and then can come up and do something different. Okay? The log is used as a guarantee that all machines either commit or don't, and that's basically our requirement here, is we want to make sure that everybody eventually commits. Notice this particular protocol could get delayed arbitrarily long if somebody crashes and takes a while to come back up. Okay? So what's the algorithm? One coordinator, n workers, the replicas. High-level algorithm description. Coordinator asks all the workers if they can commit. If the workers say vote commit, then the coordinator broadcasts global commit. Otherwise, the coordinator broadcasts global abort. Workers obey the global messages. We use a persistent stable log on each machine to keep track of what you're doing, and if a machine crashes, when it wakes up, it first checks its log to recover state of the world at the time of the crash. So if you think through this pretty quickly, this is basically what I said when I showed you a distributed state machine with durable storage. That's exactly what we're doing. And the state machine is basically tracking where we are in the two-phase commit protocol and whether we're committing or not. In fact, we can even show this as a state machine. But for a moment, I want to just drill down for a second on this. So the coordinator, there's a special coordinator, sends a vote request to all workers. All the workers wait for the vote request, and then if they're ready, they send vote commit, and if they're not, they send vote abort and immediately abort. Okay? If the coordinator gets a vote commit from all the end workers, sends a global commit to all workers, and if it doesn't, it sends a global abort. And then eventually, if you get a global commit, then we commit, and if you get a global abort, you abort. This back and forth is designed to make sure that everybody decides to do the same thing. And what's interesting, perhaps, is if you start thinking about applications of two-phase commit, when do I say commit or abort? Well, it could be that I've got my own copy of some information, and I'm going to do a bunch of sanity checks on it. I'm going to make sure things match my requirements, yada, yada, yada. You notice, remember that phone conversation we did at the beginning? Yada, 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 right? And as a result, if I've decided this is okay to commit, then I'll say commit. Otherwise, I'm going to abort. So you make sure that this won't commit unless everybody is, in fact, ready and willing to commit. Okay? So here's a failure-free example. Coordinator sends vote request. Everybody sends vote commit. We get a global commit, and we're good. All right, so that's what happens when there's no failure. Here's the coordinator's state machine. There's sort of an init state where we receive a start, and we send a vote request, and we wait. And once we have all the vote commits, we send a global commit. And if we get any vote abort, we send global abort. So it's a pretty simple state machine. Okay. We can look at what the workers have. They also have an init. When they receive a vote request, they make a decision one way or another. If they send abort or they get a vote abort, then they abort. Okay? So it's not like it's a complicated state machine, but it's replicated and it's made durable by the log. So here's an example of failure, okay, where it only affects the states in which the coordinator is waiting for messages. So here, the coordinator is in the wait state. Coordinator only waits for votes in the wait state. And if it doesn't receive end votes, it times out and sends global abort to everybody. Okay, so this is a good situation where maybe one of the members dies and just says that never responds at all. So here's an example of the worker failures. The coordinator sends out vote request. Notice that worker 3 crashed, so we send vote commit. All right. Eventually we time out, and the other ones get an abort. Now the interesting thing about this protocol is when the worker wakes back up again, worker 3, at that point it'll actually query the coordinator for what happened and find out that there was an abort as well. So it's not like worker 3 will wake up and conclude the wrong thing. We can also look at coordinator failure, where the worker waits for global star messages. In ready, coordinator fails, the worker's block waiting for the coordinator to recover, etc. So all of these, here's a coordinator failure case where nothing happens and they all abort. Okay. Coordinator failure number 2, here we vote request. We send commit, the failure dies. Eventually coordinator says, oh, I didn't get anything, I'm going to abort. And notice that because the coordinator didn't send vote abort or vote commit to everybody, it looks in his log and says, oh, okay, I'm going to abort. Now, I can only show you a few of these examples, and I don't want to bore you with too many of them, but suffice it to say that the protocol works properly with a log on all sides such that everybody either all commits or all aborts eventually. And that's the whole key. All right? Question? Yeah.
So what if the coordinator sends out a global commit, but some of the workers don't receive that?
Yeah. So the workers won't... So if some of the workers don't get the commit, they will time out and they can ask the coordinator for a retry or retransmit. But there's enough information so the coordinator has already put in his log that he's telling everybody to commit. So he will not send aborts to people, and if somebody asks him, says, well, I never received anything, he can say, oh, commit. So that the right state transitions are placed into the log to make this persistent, which is why it's a cool algorithm. Can you see what's the key problem with this algorithm? Anybody want to take a stab? This one isn't used as often as you might think, even though it seems like such a great algorithm. What's a problem with this? Yeah. Yeah, you got to wait for everyone. You're going to say something else, or same? Yeah. So the issue is this algorithm is not resilient to any participant failing. It basically has to wait for them all to work. And so that's kind of the essential problem with this. And that's why people use something else, which I'll tell you in a moment. But all nodes use stable storage to store the current state. And it's some non-volatile storage that guarantees atomic rights. And on recovery, basically, you can restore the state and pick up exactly where you left off. So that's cool. So blocking for the coordinator to recover, you can go through this. I don't want to go through it anymore, but basically you end up blocking. If the coordinator's down, everybody has to wait, etc. So why do we want to go to all this trouble? I mean, we're going to this trouble to make a set of nodes all come to the same decision, and unfortunately we've set ourselves up in a situation where one of them can fail and hold us all up. So it seems like we've got a net negative here. Okay? The reason is fault tolerance. So if we have a distributed state machine and all of the participants are participating in it, then no matter who fails, we have the right state there. And if we can fix this blocking issue, which I mentioned, then we've got a great system that could potentially continue correctly despite problems. Okay, so a group of machines can come to a decision even if one or more of them fail during the process. Okay, and the simple failure mode, by the way, here is fail stop. So when you talk about two-phase commit, you're assuming that when a node fails, it doesn't get schizophrenic and just go totally nuts. Okay, it actually fails and it stops talking. Okay, which is not a normal failure mode for people, but or computers. But the fail stop mode is the assumption here. And after the decision made, the result is recorded in lots of places, and so it's hard to destroy the result. Again, that seems like a good thing. Okay? An undesirable feature of two-phase commit is blocking. So one machine can be stalled until another site recovers. So site B writes prepared to commit to its log, sends a yes to the coordinator, and then crashes. Site A crashes. Site B wakes up, checks its log, hasn't heard anything, sends a message to A. What happened? I don't know. I crashed, and A's crashed, so it doesn't answer for a while, and eventually A comes back. You can just come up with these, long-term blocking scenarios, and that just doesn't seem good in the global internet when you want to try to have thousands of things participating, right? So block sites holding resources until it learns of the fate of the update. So if you're using two-phase commit to give you a distributed file system, the problem here is that you can only have one outstanding write when it's blocked, and nothing can make progress until everybody comes back up. So what are some alternatives? Well, there's three-phase commit. Okay? You can imagine that three-phase commit has one more phase than two-phase commit. Okay? I'm assuming you all caught that. But it does have that extra phase to make sure that it doesn't get stalled when somebody's down. So it's much more resilient to failures. The interesting thing, I will call a downside to three-phase commit, is there's still a single coordinator, just like with two-phase commit. And there's a lot of cases where you don't want to have a particular node be the only one who can coordinate. So there's many other options. One of them that's quite popular these days is called Paxos. If you take 262 with me, I'll teach you about Paxos. It's an alternative used by Google and a bunch of others that does not have the two-PC blocking problem. It also doesn't have the single coordinator problem of three-phase commit. So there's no fixed leader, and you can choose a new leader on the fly. Okay, this is another Leslie Lamport thing. It's actually a pretty amazing protocol. Literally no fixed leader, and you can somehow make progress. Some people think it's extremely complicated. Many people think it's extremely complicated, but Google has managed to implement it, we think. Okay, and they've written papers claiming they've implemented it, we think. There's another one called Raft from John Osterhout, who started here at Berkeley. He's now at Stanford, which is a simpler protocol to describe. It has some of the same properties as Paxos. Seems pretty cool. All of these, however, have a very essential problem, which we're going to address next, which is if the participants are malicious, these protocols break down. So if a participant decides to try to screw the protocol up, these won't help. These only work assuming that the only reason the protocol is not adhered to is because of a crash or a failure of some sort, not because of a worm or a virus. Okay, and that's the essential issue that you might want to worry about, which is what happens if one of the nodes is malicious. And let's face it, from an internet standpoint, we all live in a pretty malicious world these days. Lots of break-ins. The last couple of years have been notorious. Probably a third of the U.S. Had their Social Security numbers stolen a couple of years ago. Target and a bunch of big companies have all had their credit cards breached. It's basically a problem. Okay, so maliciousness is a valid problem that the question is how to address it. Right now I'm going to talk about another Leslie Lamport idea, the Byzantine generals problem, which is really targeted at a malicious decision-making process. So there's N players. Here they are, a general and 3 lieutenants. Excuse me, let me try this again. N players and N-1 lieutenants, with, in this case, it's 1 general, 3 lieutenants. Some number of these might be insane or malicious. Okay? You can tell by his brown shoes that's a malicious lieutenant. Okay, clearly. The question that you might ask is, can we come up with a distributed decision-making protocol that works despite the fact that there's some number of players who are actively trying to make the wrong thing happen? That's the question here. Okay? And the commanding general is going to send an order to his N-1 lieutenants such that we have the following integrity constraints. 1, all the loyal lieutenants do the same order. So notice the general is saying attack, and the lieutenants that are loyal are all going to attack. Notice that this malicious one is saying, well, the general actually told us to retreat, so why don't you do that instead? So notice the malicious general or malicious lieutenant is sending the wrong orders on to other lieutenants, okay? So the second thing is, if the commanding general is loyal and not crazy, then all of the loyal lieutenants are going to do what he asks. Okay, so notice that we're allowing, not only can the lieutenants be malicious, but the general himself can be malicious, which in that instance means sends different orders to different lieutenants. Okay, so, by the way, you might ask yourself, why are all these things defined in a military standpoint with generals? That just, it seems to be the way they're done. So, anybody have any questions on the consistency requirements? So the first one is that all the loyal lieutenants do the same thing. Notice that's a consistency question. Make sure they all do the same thing. And the second one is if the general is loyal, all the loyal lieutenants do what the general asks. Now, yes, question.
How do you know your general is loyal?
This is I like your question. How do you know the general's loyal? Or how do you know the lieutenant is loyal? The answer is there is no way to know at all for sure. Okay? So, when we're talking about malicious parties, the important thing to note is the malicious party can behave as absolutely maliciously as they want, which means they can, to the outside world, if an auditor is coming and seeing, are you being a loyal lieutenant or whatever, they will behave. They'll be on their best behavior the moment anybody's watching, and then they'll still send the wrong things to screw up the protocol. So there's no way in principle to know for sure that a lieutenant or a general is behaving according to a protocol. So maliciousness fundamentally means that they are going to do the worst thing you can imagine times 2, okay, to screw up the protocol. Yes?
So this one seems to be like a majority vote system.
It's not. It's if you just did majority vote, it turns out you can't make this work. You need something stronger than majority vote, but that's a good guess. If you add cryptography into it with signatures, you can make it a majority vote.
I'm wondering if you have more malicious lieutenants than like loyal lieutenants.
Well, so clearly, good question. There is a number of malicious entities for which this protocol falls flat, right? How many people think that that's got to be true? Good. There is no way that we could have an arbitrary number of malicious entities and still get a good protocol. So that's clearly going to be the case. So the question has to be, how many can we tolerate and still get a good result, right? So, again, I put the paper up if you want to read about Byzantine agreement. But there's an impossibility result that starts out, which is you cannot solve the Byzantine generals problem with n equal 3. It's impossible. And the simple thing you can see is, here's a case where the lieutenant is malicious, but the general's not. So he says attack to both of them. But you still can't, this lieutenant here doesn't know what to do because he's getting, attack from the general, and here's retreat from the other lieutenant. And that's identical to this other scenario where the general is crazy, tells the lieutenant to attack, tells retreat to the lieutenant, and the second lieutenant, who's not malicious in this case, says, well, he told me to retreat. That poor guy on the left, might as well give up now because he has no idea, right? And it turns out, so 3 is an impossibility result. And it turns out that that paper shows that because 3 is an impossibility result, it turns out what you show is that with F malicious entities, you need the total number to be greater than 3F or it won't work. Okay, so notice that this is stronger than majority. This is greater than 2/3 have to be non-malicious to make this work. And various algorithms exist to solve this problem. The original one was exponential in n, which obviously is not terribly great, but it was a great idea paper. Newer algorithms have complexity about this is supposed to be n squared, etc. So there's a Byzantine fault tolerance algorithm that allows multiple machines to make a coordinated decision even if a subset of them less than n over 3 are malicious. And again, like I talked about coordination earlier in the lecture, the idea is the request comes in and the distributed decision making is made, and what comes out is a consistent decision. So that decision could be, do we commit or abort? Or here's some data. Should that be the right to offset 35 in the file system or not? That's the decision that's being made. The Byzantine agreement algorithm helps you make that decision even when there's malicious nodes. Okay? Now, the last thing I wanted to mention in these lines is this. So blockchain is busy saving the world for capitalism, I don't know. But it's an interesting question. Is a blockchain a distributed decision-making algorithm? Now, I'm going to give you a rough idea of some of what I think is the essential element of blockchain here, which is there's lots of blockchains, but they all kind of have this idea that there's a chain of blocks. Okay, that shouldn't surprise you, right? Typically, there's a root, and there's a set of firmly chosen blocks that are backlinked with hashes, and we'll talk more about this in a couple of lectures in general. And then there's the kind of the head of the blockchain, which is in being figured out. And so the blockchain is a chain of blocks connected by hashes to a root block. The hash pointers are unforgeable. So this link here, or any of these links actually, between blocks can't be forged once they exist. The chain has no branches except for perhaps the head. That's why it's a chain. And blocks are considered authentic part of the chain when they have an authenticity info in them of some sort. And so, for instance, how many people here are familiar with how Bitcoin works? Has anybody read about it? So I'm just going to give you a really brief idea here. So, for instance, with Bitcoin, the data looks like this, and there's a bunch of miners in various parts of the world whose job it is to take transactions that are proposed, put them into blocks, and try to do a proof of work problem, which basically says that I can find some nonce data to put in here such that the hash has enough zeros in it to meet some complexity constraint. And we won't go into that more right now. You can ask me later. But what they're doing is they're burning the energy resources of the world to figure out how to get these elements linked. And the idea here, for instance, is that these green elements have a proof of work in them already. So does this hashed one. But there's still some tentativeness as to which is the actual chain head. And the one that finally wins is the longest one. The decision is made about the miners. So What's interesting about this? There's the word decision kind of crept into several times in several different statements I was making. So you might ask yourself, could I do decisions with this? Well, yes. So for instance, here's the miners. They're trying to solve the, that's not prisoner of war, that's proof of work problem. And there's an epidemic replication algorithm between them, which is basically every time there's a change, you just send it to everybody. You could imagine, and this is exactly how Bitcoin and Ethereum and all these things work, you propose some new transaction to the miners, and they send those to everybody. And then they're busy working to try to make Bitcoins or Ethereum or whatever by solving the proof of work. And they're essentially going to take the decision, and if they get their decision first, they will put that decision into one of the blocks, and it'll become cemented in the data. And so what does a decision mean here is that the proposal's locked into the blockchain. Could be a commit or abort, could be a choice of value or a state transition, whatever. And then, of course, a NAC means it didn't make it into the blockchain. And, of course, all of these systems have the ability to have a whole bunch of observers who are getting the results. And so what's cool about that is anybody in the world can verify the result once it's happened. So, yes, a blockchain is a decision-making algorithm, and the distributed scale here is pretty astounding. There's a lot of people involved. All right, so let's finish up. So in conclusion, I don't have this thing layered here, so that's fine. So we talked about a protocol, which is an agreement between two parties as to how information is transmitted. We talked about the end-to-end arguments, which is if a higher layer can implement the function correctly implemented in the lower layer only if it improves the performance significantly and does not pose burden. We talked through two-phase commit, which is a distributed decision-making process. One coordinator, a bunch of secondary folks that are committing. We talked about the Byzantine generals problem. If you want to know, the essential element of Byzantine generals is you need n greater than or equal to 3f plus 1, where f is the number of malicious nodes. And then we finished up here talking about block